Okay, this is problem 8-39. Good problem, because it's going to use a lot of the things you've learned before to solve this. What I'm going to recommend when you have something like this, I'm just going to break it into two forces here. I'm going to make this FBY and make this into FBX. It's the horizontal and vertical components of this. Now I come back here and make this FAY. And make this FAX. Okay, first thing to do would be break these into individual forces. And they would occur 1/3 from here and 1/3 from here. So to calculate that area, we would just do 1/2 times the base, which is going to be 3, times the height, which is going to be 4. That's going to give me a value of what? 6 kilonewtons. Each of these obviously be the same, so we could replace these two when we're calculating our moments right now with just two forces coming down at 6. So that's why I labeled these as 6 here and 6 here. And again, that's kilonewtons and kilonewtons. Now the distance from here to here, we would come over, if this is 3, we're going to come over 2/3 of 3 to find the centroid, so that'll be 2 from here. Now here we're going to come over 3, and then we're going to come over 1/3 of 3, so we'll come out a value of 4 here, and obviously it's going to be 6 over here. Okay, now all you have to do at this point is take a moment around A and set that equal to 0, and we can find out what this guy is. So when I do that, I did -6 times a distance of 2. -6 times the distance of 4 plus FBY times 6 is equal to 0. We'll solve that moment and you'll get very quickly FBY is equal to 6, and that's going up. Okay, now what you can do is, okay, at this point just sum the forces in the y direction, set those equal to 0. We will get 6 that we have here. We got -6 coming down. We got -6 coming down. Plus FAY is equal to 0. FAY is equal to 6 kilonewtons. Now the only thing you need to be concerned about is, since this object here, or this, I don't know what you want to call it, a member, is creating a vertical load, as a result of being angled, it also creates a horizontal load. The reason being, because if we draw this is the hypotenuse, its components are going to be like this and like this. So if we know this value is 6 coming up here, which causing the FBY, we said which was 6, then we need to find out what this would be. This would be FBX. Now we can do this with trig if we want to, but we also know the ratios. We know this is a 3 to 4 ratio because we have a 3 and a 5, so 3, 4, and 5 with standard triangle. So we can set this up as a ratio and have FBX, this over this, 6, this over this must equal to 4 over 3. We solve for that and we'll get FBX is equal to 8 kilonewtons going to the right. So now all we have to do is sum forces in the x direction. We will get -8 kilonewtons as a result of FBX plus FAX is equal to 0, and you'll find FAX in this case is going to equal to 8 kilonewtons going to the right. Alright, now at this point I've drawn where the cross section E is going to be. This would represent E. So now we can start labeling everything and we can find out what the forces are going to be. So we know this is 8 kilonewtons coming in. 8 kilonewtons come in, we have to have 8 kilonewtons going back out to have this thing in equilibrium. We have a force here, we said was what? I didn't label that as 6. So this is 6 here. Now, to find out, we need to find out what this value would be here. Since it's 4 here, we just take 4, we divide it by this total length, and then multiply it back by see where it is at this. So it'd be 4 divided by 3 times 1.5. So it'd be 4 divided by 3 times 1.5, or times 3 over 2. When I do that, I will get that value of being, what's that, 2. Which makes sense, because where it's half, it's going to be half the 4. All right, so we'll find out the area of this. The area of this would be 1/2 times the base, which is 1.5, times 2. 2's cancel out, and we get, what's that, 1.5, right? Sorry. Yeah, 1.5. So then what we know at this point would be that our shear, or this force here that's going to cause, would be, you have to go back 4.5 kilonewtons going down here. All right, the only thing we have to do now is to find out what the moment is. We're going to sum the moment at E, set it equal to 0. So we have the 6 coming this way, so we'll make anything go this way to be negative. We have negative 6 times 1.5 plus the 1.5 that we figured here, and the distance from it's going to come over here. We would be coming over 1/3 of 1.5, so that's going to give me a value of, what, I guess a half. And when we sum that value there, we will get a value of 8.25 kilonewtons going that way. So this is giving me minus, and so we know that this moment here, that goes back this way here, this must equal to 8.25 kilonewtons. All right, so now we got everything we want. So I'm going to draw a cross section of the beam. Let's see here too. What we should do now at this point is go ahead and we'll find out what the area of this beam is. Let's go ahead and dimension it. Look in the picture. It's 50 by 100. So we know this is 0.100. This value here would be 0.05. We know E is going to be located right here. We know from our picture that this distance is 0.02. So now the most important thing is to find where your centroid is. In this case, you don't have to calculate it because it's right in the middle. So we know this distance from here to here is going to be 0.03. That's very important information. So at this point, just calculate the area. Base times height. That's going to give me an area of 0.05 meters squared. Now find the moment of inertia. The moment of inertia would be equal to 1/12 times the base, which is 0.05, times the height, which is 0.100 cubed. We'll run that number there, and I think you can get 4.167 times 10 to the, what is that, minus 4th. And that's meters to the 4th power. Oops, sorry, that's -6. Sorry. Go back here. Try a small eraser. Make that to the 6th power. Okay. Now the thing to note on this, since this moment here, you got a greater moment going this way here. What that means is anything above here is going to cause compression as a result of the moment. Anything below is going to cause tension. That's what the moment's going to be. Now, as a result of this force here, we'll do that in blue, you're going to get compression, and you're going to get compression. So, to calculate what the stress is going to be there, all we have to do, the stress at E is going to equal to the force P, which we said was 8 kilonewtons, so 8 times 10 to the 3rd. We'll divide that by the area of 0.05. Now what I'm going to do is make that negative because it's compression, and again we're trying to find out what's happening here. So I'll make the moment here, since it's going to create a tension, we will do the moment, and again we said the moment was 8.25 kilonewton meters. I should have put that on there, I apologize. And that's 8.25 times 10 to the 3rd. The C value, this is important, C value is from here, from the center of the beam to this point. So from here to here is 0.03. And I divide by the moment of inertia, 4.167 times 10 to the minus 6, and you will get a value of approximately 57.8 megapascals. Now I think when I looked at the solution manual, they left, if I remember right, they let these signs be the same. But when they did the math, I checked the math, they ended up coming up correctly here. So even though one of these is incorrect in the solution manual, they did do the math right. Now that would be what the bending stress would be. Now the problem on this one is you also have shear as a result of this 6 kilonewtons here, because it's shearing across this. So all you'd have to do to find what the shear would have to be is to find basically VQ over IT would give me my shear value. To find the V value is what's cutting through here. We said that was 4.5. So shear is going to equal to 4.5 times 10 to the third. Now the Q value, and why we're doing this, is it's going to be this area here. If you want to find out this, you take the area from there out. So the Q value here is going to be 0.02 times the thickness, which is 0.05. That gives you the area. Now the distance we're looking for is from here back to the center line here, or the CG of this cross section. So that we come up 0.03 and then come back another 0.01. That gives us 0.04. Again, we come back to 4.167 times 10 to the minus 6. We multiply it by the thickness, and the thickness in this case would be 0.05. When we run that number, we will get a shear value of 864 kilopascals. So it's a very good problem. It's got a combination of not only bending stress, it has compression stress, and it also has shear. It uses all three. So look at this one carefully. It'd be an ideal test problem.